Hello everyone and welcome to Live from the Lab. This is the show where we talk about different technologies that Bruker has developed to help scientists discover the world around us. Today's topic is X-ray microscopy, specifically looking at large objects in their pristine condition. Now this can cause some serious issues with a classic Micro-CT or X-ray microscope because a lot of the magnification comes from geometric means. So you really have to have the right tool designed in the right way. So that means higher power, that means large detection, and it also means the ability to hold samples that can be quite heavy in a very stable condition, so that during the rotation and the subsequent data collection, that sample stays perfectly still. Now, in order to learn a little bit more, we've put together a video. So here we are, and we're going to talk a little bit about the 1273 and specifically that high capacity. So I'm joined by my colleague, Dave. Thanks for joining us. Good morning. So the 1273, that's kind of a fun machine, huh?
Yeah, it is. There's, like I said, it's a large object, so very little sample prep goes into this. Yeah. No cutting samples down. You can basically just stick a large object in there and hit go.
So everything from, this is actually that big rock that we had measured, so pretty substantial.
Yeah.
Here we have a skateboard wheel. Here we have some sound deadening material shaped like a plant.
Right, and you've got all densities too. Yeah. Rock is actually fairly high density, and metal bearings, and then you have very lightweight fabric.
So when it comes to measuring samples of varying densities, what are the challenges involved with that?
The challenges is matching the frequency or the energy to the material.
Okay.
So for higher density material, you have to go up and use higher energies. And for lower density material, lower energies. And then the problem arises when you have soft and hard that you then have to kind of pick a balance. You know, when you have high density and low density material, you have to pick some sort of balance depending on the information you want to extract.
Okay, so, and we're going to look at the data from this in a second, but since you mention it, here you have that skateboard wheel, and that has both high density metal bearings and then also plastic. So how would you approach that in terms of an experiment?
Well, if I want to look at the bearings, which I did in this case, then I'm going to use a high voltage and a thick filter to screen off the lower energies, so to get rid of the beam hardening effects and to some of the scatter. Because when you're using low energy X-rays on a dense material, you'll get scatter. And it causes some artifact. So by putting filters in place, we remove that the low energy X-rays, and it gives us a cleaner image. If I wanted to actually image the low density material, it's possible. I have to use a lower energy.
Okay.
I will see some of the material, but I will get a few scatter artifacts off the metal.
So the issue will be that as this is turning, that metal will also be shadowing.
Correct.
Right.
I mean,
Okay.
every angle, you're going to get a diffraction, a perfect diffraction off every surface because you have a round object.
Okay. So in terms of then that power level, so that we say high power.
Yes.
What does high power mean in the instance of the 1273?
1273, so 130 kilovolts, 39 watts. So it's a little bit more than our other bench tops. Yes, there are systems that will do hundreds of thousands of kilovolts, but not bench tops.
Right. And so the kilovolts are important because that's your penetration power.
Correct.
Okay.
Correct.
But then the wattage is important
for photons through flux.
Okay, so you get the flux, so you can get an image in a good period of time.
Exactly. You want to take a good image as quickly as possible.
All right. So now in terms of kind of the whole different variety of instruments, like you mentioned, there's other machines that can go, say, higher kilovolts.
Right.
There's some that do other things well. We have, benchtop, like the 1275, push button,
Right.
just high throughput type machine. 1272, that one we had talked about in a previous live from the lab, and they were talking about higher resolution. The identity of this machine?
Large objects.
Large objects.
Yeah.
Okay, so it's all about the capacity, the big things.
Large objects and more punching power.
Okay.
Batteries.
All right, so batteries.
Yeah, batteries are great.
That's a pretty hot topic. So.
Yes, it is. We've done a lot of battery work with the system. Again, it gives you the size for larger formats.
Okay.
And it gives you the punching power to get through a multi-cell battery, a big pouch cell, or a big jelly roll.
Mm-hmm. And so there we'd be looking at things like the particle size, shape, cracks.
Exactly. Looking at the electrodes, looking at the dispersion of the electrolyte, uniformity of the roll, and looking at the top the connectors coming out.
All right. So now, in the previous episodes, we had talked about how we use CMOS detectors for the higher resolution side. Now, this has a flat panel detector, right?
Right. It's still a CMOS.
Okay.
It's just not a scientific CMOS.
All right.
And there's subtle differons on how the data is collected, but it's still a CMOS detector.
Yep. And a really big detector.
It's a large format.
All right.
You saw it on the video. There's a couple images there.
All right, so you've brought actually some data from a few of these objects, right? So we can look at that on your computer?
Sure. So this was the skateboard wheel,
Yep.
and you can see we have a nice, you can see the races. You can see there's actually two sets of bearings in here.
Okay.
They come through quite nicely. And then we have it up here in 3D. So I was able to, render it nicely in 3D. You can see it's jumping around. Oh, there's the network lag.
So in terms of generating the data then, and here we go.
Here we go, yeah.
So the first step, of course, with any of these X-ray microscopy experiments is that you mount it in the machine.
Right.
And then did you mount it this way or this way?
I actually mounted it that way.
This way?
Yep.
And then we...
yeah, you always want to shoot for the thinnest axis.
Yep.
And so if I were to do it this way, I'd be going through the metal this way,
Yep.
and there's less metal that way, so it's going to give you a little bit better image.
Okay, so we measured it like this.
Yep.
And how long did that data collection take?
It was about 4 hours.
Okay, so about 4 hours, and you can see here, I mean, just the amazing resolution. Now, of course, here we see the outside surface.
Right.
And you can see kind of the surface quality, things like that. What other types of information would people be interested in here?
For something like this, you would be looking at like maybe contact patch. You want to maybe look at what's going on the inside of all this. Is there dirt in here? Are there defects? You could dive into it and start looking kind of at the metal uniformity, things like that.
Okay, so we could actually see even, are we getting uniform wear?
Uniform wear, exactly.
Okay, or are you getting particulate?
Right, and if you're doing some sort of, this is, I know these are pretty good, but if you're doing a failure analysis on a part where you didn't have access to this material, you might want to stick something like this in, then you can image it on the inside without having to take the assembly apart.
Okay, because then this could, I mean, conceivably, you could put this right back into service. We
Yes,
haven't had to
absolutely.
cut it, take it apart, anything like that.
Yep.
But the cool thing is you do have the power with a machine like this to shoot through and image the internal structure of the
that
metal.
was actually straightforward. Yeah.
Okay. So then the next sample you have was actually this sound dampening material that's shaped like a plant, huh?
Yes, it was actually, it's a marketing material from the company that produces this. And so sound deadening material is actually just a fibrous material with voids of different spaces, so it deadens and absorbs different ranges of frequencies of sound.
Okay.
And so, like I said, it's lots and lots of fibers. So here we can see, we can do lots of statistics on these fibers. We can tell you orientation, we can tell you density, thicknesses. But then I can also come in here and pull up. Now this is the volume of the space between the fibers.
Okay. Okay.
And that's just as important. And say, I mean, this is for sound deadening, but people do this for other filters, for fluids, for gases. And then you want to look at this because this dictates how well things flow through your material.
Yeah.
And if you have like a hole or something like that, that would actually defeat the filter. So you want to be able to inspect the filter to see if there's any voids, defects, uniformity within the filter. Yeah,
I mean, one of the most amazing samples I think I've seen was, or in terms of capacity, was that oil filter that you had measured.
Yes, we measured an oil filter for an engine manufacturer, and we were able to image the whole oil filter, remove the metal digitally, so we just had the paper inside, and then we were able to count metal particles stuck inside the paper filter itself.
Yeah, so I mean, real game changer there, because the traditional method might be that you have to somehow, take it apart, and then you'd have to extract the metal.
Right.
And
yeah, they were cutting them open, and the cutting process generated the same amount of material as the actual sample.
Whereas in this case, you could actually imagine taking the filter now, you measure it, see what the particles are, take it out, put it back in, run it for a certain amount, and then you can determine really over that duty cycle the accumulation.
Absolutely, absolutely.
So. And really, for that sample, it's about both capacity and also the penetrating power, right?
Exactly, yeah.
All right. So now composites, though, like you had mentioned, or the fibers and stuff, that's also a really big thing. I mean, carbon fiber, all that type of thing.
Fuel cells, carbon capture, membranes. We've done a lot of work for filter companies, membranes, water filters, underneath your sink, your RO filters. Stick the whole thing right on in. We can scan it. And in that case, they wanted to look at the manufacturing process for defects, but you could see all the paper and defects and particles inside the paper.
All right. So in terms of that water filter, for example, again, if you had run it for a while, you could probably also image, say, deposits of the different minerals and things like that in it over time.
Yeah, all the big chunks that come through your pipes.
All right. So if anybody has any questions, by the way, you can always send them in if you're watching this broadcast later. The email is live.events@bruker.com. Otherwise, right now, if you want to get them answered, you can type them on the right side of your YouTube screen. Just type them in there, and then we'll get to them at the end of our discussion today. Now, the machine itself, though, it is benchtop.
Yes.
But it's pretty big, right?
It's a big benchtop.
So we're talking like about 4 feet long?
Yeah.
And about, was it 2 feet tall?
Yeah, 2 feet tall.
Yeah. So it's interesting because it's that benchtop form factor and somewhat portable. And so we actually had a pretty fun experience.
Yes, we did.
Recently, or I should say, in the last few years.
I was just there. I was there a couple weeks ago. Yeah.
So yeah, I mean, we were able to go up to a little island in Canada where they're doing some hunting and archaeology work and stuff like that. Yes. And so that was a pretty fun experience, huh?
Yeah, that was a great experience. They're doing a lot of good work with that system up there.
So speaking of kind of that cultural heritage application, this type of machine is perfect for it because you can measure things in their pristine condition.
Absolutely. Like big pottery shards was a cool project I did.
And so one thing that we learned, too, is that this really helps the conservation process because we're able to help guide that, right?
Right. You can take this concretion that you have no idea what it is, stick it inside the instrument. In that case, they run it in what's called a continuous mode.
Yeah.
Where they just do a very quick circle and they like a 2 or 3 minute scan, and it's not the highest quality image, but it's fairly good. And then they can look at this concretion to say, is there anything of value in there? And
Yeah.
and then if there is, then they can pass it on to the conservator.
All right, because sometimes you might not know what you end up losing when you remove
Exactly.
that debris.
Coins. We've been able to read like the dates and the faces off of a coin in like basically in its concretion and its muddy form, and say, is this a 1700s coin or is this, 10 years old?
Right, right. And there, I mean, you can just imagine that process of removing the concretion, removing any of that debris can actually cause damage or remove the information.
Right, you can actually remove material off the surface of the coin and stuff.
So you mentioned this continuous scan.
Yes.
So now how does that differ from a traditional scan?
So we have two modes, step and shoot and continuous. And step and shoot is what I use most of the time. And that means you take an image, a second, say, and then you rotate whatever you have it set, 0.1, 0.2 degrees. You stop, you let it settle, you take image, stop, settle, and you do that all the way around.
Okay.
In a continuous mode, you basically collect data as fast as you physically can, and you just let it slowly rotate.
Okay.
Like I said, it's not quite as sharp because you're not settled, things are moving, but you can take very quick scans, 4 or 5 minutes, and get good quality, at least for screening purposes.
So the benefit, like you said, very fast, and you do get that screening effect. Downside, since it's not settling at a certain position, since it's moving, you get a little blurring.
Correct.
Okay.
Yeah.
Now, how long, though, like what kind of time savings are we saying there?
So 4 hours versus 8 minutes, 6 minutes.
Oh, wow.
Yeah.
So pretty quick scan.
Pretty quick scan.
Yep. Now, the thing to think about, though, is even in that case, we do take a lot of data, right?
Oh, yeah.
Yep.
Now, when you're doing the continuous mode, it's kind of like when you go to the doctor, they don't go, jung, jung, jung. It's a big continuous scan. They just pump as fast as they can, collect as fast as they can. Yeah, you are still taking thousands of images in the course of a few minutes.
All right.
60 frames a second.
All right, so we do have some questions that have come in before. And the first question is from Susan, and that question is, what is the maximum size of an object that you can put in this machine?
10 inches by 10 inches, I think is what our spec says.
Okay.
We can obviously fit that in there. And as you like to say, a 5-gallon bucket.
Yep.
So, yeah, laptops, we've stuck laptops in there.
And just because it's a 5-gallon bucket doesn't mean that you necessarily have a filled 5-gallon bucket.
No.
Because now we're going to talk about penetration power, right?
Right. So, yeah, filling it with water, you wouldn't get through it.
Right. So, and that's always going to be the balance here, is that you can have very large objects, and if it's a very low density object, you can shine through it.
Right.
And then there's also the balance of resolution, right?
Right.
So larger objects.
Right. We use geometric magnification, which means the closer you can get to the X-ray source, the greater the magnification.
Yeah.
So if you have a small object, you can magnify it, and, because you are magnifying it to a fixed size.
Yeah.
And if you have a big object, well, then that big object has to fit on a fixed number of pixels. And so basically it limits if you want to image the whole sample, it limits ultimate pixels voxel size is going to be the sample diameter divided by the number of pixels you have in the horizontal direction.
All right. So on that note then, what would kind of the ideal size on the small end be in order to get the best resolution on the machine?
Say a AAA battery.
Okay.
That's about, you can go smaller than that. Like we always love a toothpick. Toothpicks are really kind of our standard go-to image. But like a AAA battery basically matches the ultimate resolution of the detector. So you can get like down to about 3 micron voxel with a AAA battery.
All right. And in terms of material set and the power side of things and the versatility, I mean, we were shooting through this metal bearing, no problem. Huh?
Yep.
So things like that, you're fine. But then on the low end, you're also okay with
Yeah,
light
I think I shot this one like at 35 kilovolts, and it'll go down to 25 kilovolts.
Okay.
So it does give you that broad range of lower density and high density punching power.
All right. So then another question that came in here from Matt is, in the video, we actually showed multiple samples. Are you actually able to sub-segment the scan?
Yeah, you can. So, like I said in the, we showed all the sample stack. Yeah, I can go through. And there's a couple of places I can do it. When I'm actually reconstructing the data, I can just pick off each segment and process it independently.
Okay.
I can also process the whole thing and do it later on in the data analysis software. I can pick off various sections.
Yeah. So there would actually be two ways approaching that then. One is you could collect all the samples simultaneously, especially if they're very similar, you know, if you're just characterizing out of a batch a bunch. Or if you have a different type of sample in the image, you could actually collect each at different conditions.
Yeah. So I can set up a batch file.
Yep.
And I can set the imaging conditions for each independent one and its location. And I can just store that into a batch file, and then it'll image each one independently under each condition. So you'll move it forward, move it back, you know, anything you want. Different filters.
Yep. And so, and in there, the little plastic thing, so it's just something we printed up, but the trick is you need to have the plastic be low density, but also stable.
Yes.
Right? So things aren't moving on you.
Things aren't moving. I told you this morning, I did some chocolate, and it's just starting to melt towards the end of the run.
All right. So that is all the questions that have come in, and we're at the end of our time. Thank you, Dave, for joining us today.
Thanks for having me.
So it's always great to learn all those things, and thanks everybody out there for joining us. So until next time, make sure to keep your signal high and your background low.